Hello everyone, my name is Xingyu, and today I will present our paper, SoftGym, Benchmarking Deep Reinforcement Learning for Deformable Object Manipulation. This is joint work with Yufei, Wang, Olkin, David held at Carnegie Mellon University. Robotic manipulation of deformable objects has wide application both in our daily lives, such as folding laundry and preparing food, and in industrial applications such as packaging or handling cables. Manipulating deformable objects also has long been a challenge in robotics due to its high-dimensional state representation, complex dynamics, and visual observations such as self-occlusion. Recent works have been exploring the challenges in deformable object manipulation using reinforcement learning. However, these works often evaluate on different tasks, simulators, and robot setup, making it hard to compare among different approaches. Currently, there is no existing benchmarks for manipulating deformable objects. In this paper, we present SoftGym, a set of benchmark environments for deformable object manipulation. We build our environments on top of the NVIDIA Flex simulator that can model rope, cloth, and fluid under a unified particle representation. Our environments have standard OpenAI Gym API for interaction with our agent and have Python interface for modifying the environments. Our benchmark are split into three categories: medium, hard, and robot. For SoftGym medium, we provide 6 tasks, as visualized on the bottom left here, including manipulation of fluid, rope, and cloth. More challenging tasks are provided in SoftGym Hard, and SoftGym Robot provides the option of including a sawyer or a Franken robot. We use pickers as an abstraction of the gripper and grasping in all the cloth and rope environments in SoftGym Medium to focus on the challenges that are induced by the deformable objects. To provide more understanding about the challenges of manipulating deformable objects, we benchmark a few categories of methods. The first category is dynamics oracle, where we assume knowledge of the dynamics by using the simulator. Here we use the cross-entropy method for planning. The second category are state-based oracles, where positions of the particles, such as particles on the cloth or the fluid particles, are known. The full state oracle takes positions of all particles as input, and the reduced state oracle takes a hand-defined reduced set of states as input. For example, in the fold cloth task, we use the positions of the 4 corners of the cloth as a reduced state. Both methods use soft actor critic to train a model-free agent. The first 2 categories are called oracle because neither the states nor the dynamics are known in a real robotic application. In the third category, we benchmark several states of our RL algorithms that operate directly on images, including a model-based agent, planet, and 2 model-free methods with data augmentation, SAC CoRL and SAC Dr. Q. We benchmark these algorithms on SoftGym medium tasks. Here, we show the learning curves of different algorithms on evaluation set through the course of training. The y-axis shows a normalized performance metric for each task, where a task is considered solved when the agent reaches a performance of 1. First, as shown by the black lines here, we found that the dynamics oracle method with EM works very well across all tasks and nearly solves most of them. SAC with a reduced state representation works reasonably well in some tasks, but is worse than the dynamics oracle. Directly using the full state representation performs very poor, as the full state representation can have thousands of dimensions, and the dimension can vary across different variations of the task, creating difficulty for the RL agent. Finally, we show that for methods taking images as input, the performance is worse than using a reduced state oracle as well as the dynamics oracle, showing much space for improvement in this area. Here, we show visualizations of the learned policy on 2 tasks, transport water and spread cloth. We see on the left that the dynamics oracle performs well across different variations of the tasks, while the image-based method performs poorly. Please see our paper and website for further analysis and videos of these methods. We do a side-by-side comparison of the pickers used in our benchmark with a real robot setup. Here, the left shows the picker picks up a point and places it on a random location, and the right shows a sawyer robot repeating this motion. We can see that the simulation result is very close to the real-world result, suggesting that our benchmark can reflect the challenges in real robotic application. In conclusion, here we present SoftGym, a set of benchmark environments for deformable object manipulation. On one hand, we hope our benchmark can speed up research progress in this area by allowing researchers to build on top of existing methods, test new methods, and easily compare them in a controlled simulation environment. On the other hand, we provide analysis on existing state-of-art RL methods and show that manipulating deformable objects presents a large challenge for these approaches. Finally, we would like to thank NSF, DARPA, and LG Electronics for their sponsorship on this project, and thank you for watching.